Good afternoon, folks. Good afternoon, good afternoon. All right, hey folks. Okay, as a reminder, just when you come in, let's set our pronouns in our names. Wait a couple more minutes for some classmates to show up. Hello there, Yusuf. Hello, Barrier. Okay, let's see. All right, folks, I'm going to get started, even though we're still missing a couple of people. I just want to make sure that we're getting as much time as we can for getting information in. As a reminder, for those of you that just joined us, if you would not mind just changing your name on Zoom to make sure that it includes your pronouns, that would be fantastic. Right, and if you are bold enough to keep your video on, that would be great. This way I don't feel like I'm just talking into the void. All right, let me see here. I'm going to share my screen. Okay. Hello, everyone. Hello. Okay. So before I get started, does anybody have any questions, anything from last week that they wanted to address, or?
Hello, sir, Professor.
Hello. Hi, Yusuf. How are you?
Good. Last week's first class, it happened before I signed in. I signed up for the class. I think I sent you an email yesterday.
Okay.
I'm still getting acclimated to the whole distance learning thing with the technological.
Sure.
Yeah. So like the assignment for last week, I just saw like the lectures for last week.
Yes.
It's Scp140 1.1, right?
1.1 and 1.2, correct.
That's the last week's lectures combined.
Correct. So,
okay.
Yes,
I will look through those, and please, I will email you, and I hope you don't mind. This is actually my first meeting since, so I'm trying to like understand the homeworks and like still trying to adapt to them. So
yeah, not a problem at all. You can just let me know if you ever have any questions. You send me an email. I wasn't able to check my email since yesterday, so I'll get to that soon.
Okay.
Each week, essentially, I'm giving 2 lectures at 2 different times on Monday, one for the afternoon section, one for the evening section. And instead of giving the same 3-hour lecture or 2-hour lecture twice in a row, I'm giving half of it to you, then posting the video. The second class gets to watch that video before their meeting, And then when I meet with them, I record the second half of the lecture and I post it to Blackboard for you all to watch before we meet the following Monday. So this is now lecture 2.1. All right, if you weren't able to look over the homework, Alex, not a problem. You still have the rest of this week. The homework, the first homework set is due on Monday night. All right, so you've got a little bit of time. All right. And just, let's see, one last reminder as we get started. Good afternoon, everyone that just joined. Please just, again, change your name on Zoom to include your pronouns. Okay, Alex, stick around at the end of class and then we'll talk about that. Okay, so today we're going to talk about understanding the night sky and making sense of where things are and how things move, right? That's going to be the big focus for today. So before we talk about mapping the sky, it probably would behoove us to talk about mapping the Earth and what sort of coordinate system we use to talk about points on a spherical surface, right? So it's not like we're looking at a two-dimensional map on a sheet of paper. We're looking at a three-dimensional object in this case. And the coordinate system that we use is probably one that you've heard of. I can't speak to how well you are familiar with it, but I am sure that everybody here has heard of latitude and longitude before. So if you're looking at the picture on the left, those red and blue lines that wrap around the Earth, they are called lines of latitude. And these lines are, as I mentioned, parallel to the equator. They do not cross each other, right? So if you're looking here, you know, we're only facing one side of the Earth here. But these lines wrap around on the far side of the Earth as well. So there's, you know, there's half of the Earth that we can't see from this image on the left. Oop. Did not mean to click. Let me go back. There we go. Okay, so the Earth is a sphere. When we talk about spheres and circles, oftentimes we talk about angles. And there's a certain angle that is often brought up, that's 360 degrees. 360 degrees is the number of degrees within one circle. So I'm gonna get on my iPad here and I'm gonna pop back and forth between PowerPoint and my iPad so I can draw some stuff out for everyone to maybe help you visualize this a little bit better. Let me just jump in over here. New share, boom. Okay. This always takes a couple of seconds to get this turned on. Ooh. There we go. Okay. So here's the Earth. And we can take the Earth and we can slice it in half. Okay, we slice it in half in this particular way, directly across. This line here is called the equator, and it separates the northern hemisphere, the northern half of the Earth, from the southern hemisphere, the other half. And at the very top of the northern hemisphere is the North Pole. This is where Santa and the elves live. And at the bottommost point of the southern hemisphere is the South Pole. Right? These 2 points are important because Earth's rotational axis passes through these poles. Right? The Earth basically, you could imagine, sort of spins around like this, almost like twisting a lollipop on a stick. Right? And so the equator is this widest part of our sphere, of our Earth. Now, if we could sort of look inside of the Earth, sort of maybe look at this a little bit more three-dimensionally. Let me just go back to adding the equator in over there. Right? You could put a point at Earth's center. So this is the center of the Earth, this dot there. And we can walk from the equator all the way up to the North Pole. Right? And if we do that, then when we draw a line from Earth's center to the North Pole, it makes a 90-degree angle with the equator. Gabriel, it sounds like your mic is on. If you wouldn't mind just muting it, I'm getting a little bit of feedback. Thank you very much. All right, so there's a 90-degree angle there, and thus the North Pole's latitude is 90 degrees north. We have to specify that we're talking about 90 degrees north because there is a 90 degrees south. Right? Had we walked the other way to the South Pole, we'd end up at this coordinate. So in terms of latitude, right, the maximum latitude is 90 degrees north, and that's actually rather, I probably shouldn't say maximum, but one extreme is 90 degrees north and the other extreme is 90 degrees south. Right, so you can have any latitude within this range. Right, so you can go from 90 degrees north to 80 degrees north, 70, any number in between. You know, and for most of us, I would imagine, who are currently located in Queens, we are probably somewhere around here. This is the location of Queens, New York. And our latitude is about 40 degrees. Well, how is that determined? Well, if you look at the angle that is made by a line connecting our location on Earth's surface to the center, and the angle that that line makes with the equator, this angle in here is a 40-degree angle. All right, so that's how we're determining our latitude. This is 40 degrees north of the equator. We also have these lines that run vertically, or they look to run vertically on Earth's surface. These are our lines of longitude. I'm going to go back over to, actually, before I go back to the other slide, I'll just draw it on this. So we have these lines of latitude, which I'll draw in here. Lines of latitude do not cross each other. I'm just drawing an arbitrary number of lines just so you can get the idea. But then there are these lines of longitude, and they are long lines. They run from pole to pole. These lines are different in that they intersect at the poles. While lines of longitude run east-west, these lines of latitude run north to south, right? And together, you see that we sort of end up with like this, it's not quite a square grid, but you can see how we've got like these boxes in here, right? We can like pick out specific points on the surface, And we can describe it in terms of a coordinate, a latitude coordinate and a longitude coordinate. So let me go back to my PowerPoint here. Why is this useful? Why are we talking about latitude and longitude? Well, again, mapping the Earth is one of the ways in which we're going to talk about mapping the sky, right? It's sort of the analogy there. All right, so we have these two important lines when we talk about the Earth's coordinate system. We have the equator. That is the 0-degree latitude line. The equator is very important because it separates the two hemispheres, the northern and the southern hemisphere, from each other. The other important line is a line of longitude, the prime meridian. We use these lines of longitude when determining time zones and for separating the eastern and western hemisphere. But in any case, these are the two important lines that we talk about, right? So we have the equator, which is 0 degrees latitude, and the prime meridian, which is 0 degrees longitude. All right, so what does that have to do with mapping the sky? Well, when we look at the sky, right, you can imagine being outside on a dark night, looking up at a starry sky, and you can't really tell how far away certain things are, right? You can't really tell which stars are nearer to us or which stars are farther, but we can tell how big things look, right? Like we can look in the sky and see how large the moon is. We could look at the sky and see how large the sun is. Not that you should be looking at the sun with unprotected eyes, but I'm sure everybody here has probably glanced at the sun once in their life. You could look at, planets in the sky and see that some of these bright dots look a little bit bigger than others, right? And so when we talk about things in the sky, we can measure how big they are using angles, right? Angles having to do with like how much do you have to turn your point of view to be able to see something. All right, so in this first picture here, you can see that this person is looking at the moon, and the moon is about a half a degree across from one side to the other. Again, this is based on the idea that if you were to turn around, if you were to stick your arm out and point in front of you and do a full 360 degrees, that would get you back to your starting point. Right? And so you could look across the sky and turn, and you could see how many degrees you have to turn to be able to capture that whole object. So again, the moon is 1.5 degrees across. The Big Dipper, between these two particular stars, which are useful in determining the direction of the North Pole, the North Star, they are 5 degrees apart. If you're in the southern hemisphere, maybe you're on a vacation and you look into the sky and you see this particular asterism called the Southern Cross. We'll get into what an asterism is in just a little bit. That's 6 degrees from one star to the other, right? So angles are important, especially when we're talking about mapping these surfaces, right? We're sort of treating the sky as a flat, not flat, but as a perfect sphere, right? More on that in a moment. Okay, so in terms of angular size, right? Angular size is what we were just talking about. Something is this many degrees across. Again, a full circle has 360 degrees, but when you're talking about like things that are real, when you look at a patch of sky, there are so many stars and galaxies in a small patch that are not even visible to your eye, so you wouldn't necessarily know that they're there. But if we zoom in on the sky and we're looking at things that are between degrees, how do we accurately describe their location? And so we have a breakdown, right? We take 1 degree and we break it up into 60 arc minutes. It's not a time, even though it has the word minutes in it. An arc minute is a unit of distance. It's telling you how much you have to arc to get from one point to another. An arc minute can be divided into arc seconds, right? 1 minute is 60 arc seconds. These numbers were chosen intentionally to make it easier, I would imagine, for people that know how to tell time. Right, and so you can sort of see here that we can take 1 degree of a circle and break that 1 degree up into 60 arc minutes. But then we could take one of these really small arc minutes and break that up into 60 arc seconds, right? So we can really talk about like very small and accurate positions and sizes of things on the sky. And as it turns out, we all actually have these sort of built-in meters for angular size, right? We have these built-in measuring systems. If you take your closed fist and you stick it all the way out, so it's a full arm's length away from you, from your point of view, looking at the bottom to the top, this is about 10 degrees across my field of view, right? Well, if you were to look straight up, and this, I'm asking you all to type an answer in the chat here. If you were to look straight up, how many degrees do you have to turn your head to look at what's on top of you? What angle is this?
$45.
Okay, I got 45, I got 180, I got 90. All right, we got a bunch of angles here. Got some more 90s. Yeah. So this angle here is 90 degrees, right? And if you think about this, so if you've ever heard of the expression do a 180, what does that mean? Has anybody ever heard that before? Do a 180? It means, yeah, Jasmine's got it in the chat, right? To do a 180 means to turn around and do the opposite, right? So a 180 would be this, right? I've turned 180 degrees. I have flipped around to look the other way. If I do another 180 degree turn, I've just completed a circle. So what's 180 plus another 180? That's 360, right? So 360 is a full circle. Well, if going from this direction to that direction is 180, then what's half of that? Right? What is this angle? Right? If this is 180, then this has to be 90, half of that. Right? So from looking forward to looking straight up is about 90 degrees. Now I'm making the claim that with an outstretched arm and a closed fist, this is 10 degrees. So I'm trying to hold this so that the bottom of my fist lines up with my sort of horizontal view, my view of the horizon. My claim is that I should be able to stack 9 fists on top of each other to get me to look straight up. Right? If each fist is 10 degrees, 9 of them would give me 90 degrees. I should have my hands pointing straight up in the air. So let's see if that's correct. And you can try this too, because your cameras are off and nobody's judging you. All right, so I got 0 degrees, 10 degrees, 20 degrees, 30, 40, 50, 60, 70, 80, 90 degrees. All right, so that's a fast way to sort of estimate Remember the key word here is estimating angular size. Is that exactly 90? Maybe, could be a little off, but it's about 90 degrees. If you were to outstretch your hand from pinky to thumb, that's about 20 degrees, right? That's like 2 fists. If you take, one of your fingers, one finger is 1 degree. All right. The idea, if we go back a slide or two, right here, we said that the moon is 1.5 degrees across. That means that you could take your finger and cover the moon with the width of your finger, right? You could totally block out the moon by holding your finger up to the sky at night, right? So you can try that and verify that that works. Okay. So latitude and longitude, right? We use this sort of spherical coordinate system, right? To sort of describe direction, right? To identify specific locations. Now I'm going to introduce 2 concepts right now. They are related to, but are not the same as each other. The first concept is the local sky. Everybody has their own unique local sky. And your local sky moves with you as you go to different parts of Earth's surface, right? So from wherever you are standing, there is a dome around you. Not a literal dome, but sort of this imaginary dome on which the sky exists, right? The sky is like this giant dome around you. And the lower half of this, what looks to be a sphere in the image, the lower half is being blocked out by the ground. Or we could say by your horizon, right? You can't, if you look out horizontally in all directions, you can't see the sky below the horizon. The ground is just blocking your view. And so we've got all of this sky above, the ground blocking our view of anything below the horizon. And we've got a couple of important things to point out here, right? A couple of important positions on your local sky that are worth noting. One is called the zenith. The zenith is the point that's directly above your head, right? The zenith moves with you. So wherever you are, everybody here is in a different part of New York City right now. Some of us may even be outside of the city. Wherever you are, if you look straight up, the point directly above your head on the sky is called the zenith. That is your zenith. And your horizon is not the same as somebody else's horizon, because where you are limits what you can see and what you can't see. Right, so you've got the zenith above you, you've got the horizon in front of you on all sides. Then we have what's called the meridian. Right now, if you think back, I'm actually going to go back a couple of slides to our latitude and longitude. All right, our prime meridian runs from the North Pole all the way down to the South Pole. This is the prime meridian, from the North Pole to the South Pole. And all meridians, you can see, run from north to south. North to south. So on your local sky, there is a line that runs across the sky, which is called your meridian. And the meridian connects north on your horizon to south on your horizon. So if you look at this picture here, you can see that this person is standing in the middle. From wherever they're standing, they can face north. Let me get out my pen here. They could face north. They could face south. They could face east. They could face west. But the meridian runs from north all the way up, passing through their zenith and down on the other side, touching south. All right, and everybody has this meridian. Okay, so if we wanted to describe a direction, there are two ways that we can give that direction. If we wanted to describe a point on the local sky, there are two things that we need to include to do that. One is what's called the altitude. Right? The altitude is an angle. It's an angle measure of how high something is above the horizon. So you can see here that this person is looking at a point on the sky right around here, where this dashed pink arrow is pointing. And if you look at the angle that that line makes with their horizon, that's a 60-degree angle. So this object, whatever is in the sky at this point, has an altitude of 60 degrees. If something were directly above you at your zenith, you would say that it has an altitude of 90 degrees because it is 90 degrees above your horizon. What do you think the altitude would be of something that's on your horizon? So I'm going to draw a spot here. Let's say that we were looking at this tree, this red spot here that I just drew. What's the altitude of that spot? You can type your answer in the chat. And I'm just to clarify, this, I know that it looks like a really big blotchy spot. It's meant to be like right at the bottom where the brown disc touches the blue sky. What is the altitude of this spot? That's okay, Barrier. Okay, all right. 70, 75 is a bit of a ways off. 10 was closer. I would probably venture to say 0. The altitude of this red dot is 0 degrees because it's, look at the definition for altitude. It's a measure of angular distance of a point above or below the observer's horizon. It's how above or below the horizon are you? This point that I drew is on the horizon. There is no angle with the horizon. It is 0 degrees. Whereas the zenith has an altitude of 90 degrees. All right, so altitude's important. Right? Altitude is how high something is above the horizon in terms of an angle. The other component to describing where something is the direction that your body has to be facing, right? Because I can be looking due east at an altitude of 60 degrees. That's not the same as looking due west at an altitude of 60 degrees. Oh, let me close the blinds here. Okay, just get the lights going. Sorry, everyone. Okay, it's all better. All right, so these directions that we have, how do I erase? I hate using a PowerPoint to write on stuff. Okay, so we have two angles here. They're actually kind of hidden. One of them is the angle above the horizon. So like this angle right in here for the person who's looking, this angle here is 60 degrees of altitude. The other angle is is with the ground, right? With the cardinal directions of north, east, south, and west. So see this line, everyone, on the bottom here? This person's body is facing somewhere between the directions of south and east. So they are facing, let's just say that they're facing southeast, okay? They could also, what if, and I'll do this in a different color, what if the person were facing southeast, but a different southeast? What if they were facing this spot on the horizon? That's technically southeast also, isn't it? It's not the same southeast, but it's still southeast. So we have to be more specific. And we can start to talk about angles on this sort of disk surface that we're standing on, right? How much do you have to turn to face a certain direction? And then how much do you have to look up above the horizon? And those two angles in combination will get you to point towards any object in your sky. Right? Is there anything that I can clarify before I move on? Or is everybody gathering what I'm saying here? Okay. Very good, very good. Thank you, Jasmine. Thank you, Alex. Okay. So the first concept that I mentioned was the local sky. The second concept that I'm mentioning is the celestial sphere. And this is where things start to get a little wonky for people that are not particularly spatially coordinated. All right, so if you have a hard time sort of picturing motions of things without actually seeing them, this might feel like it's a little daunting, and that's okay. All right, just do your best to try to wrap your head around this and ask questions if I say anything that confuses you. So we mentioned before that Earth has a latitude, longitude coordinate system, right? There are lines that go around the Earth that are parallel to the equator. And then there are lines that cut from one pole to the other, and those lines intersect at the two poles. So the idea here, the celestial sphere, is imaginary. Okay, it's not like there's actually a sphere around us, but we can sort of map things on the sky as if they were points painted on this sphere around us. And it doesn't matter how far apart these things are or how far away they are, right? Like, if you're looking at the image here, here are two stars. Let's just assume that these are stars on the celestial sphere that's drawn in this picture, right? So the sphere, first of all, is around the entire Earth. This is different than the local sky, because remember, the local sky is just around you. It's half a sphere. The celestial sphere is this entire space and sky around the Earth. Now, back to these two stars that I'm pointing towards with my mouse, this is where they fall on the sphere, but we don't know how far away they are, right? Nothing about the sphere tells us the distance to these objects. It just tells us where to look in the sky to be able to see them, right? So like, well, all right, let me, I'm not gonna say anything else about that. The sphere sort of developed from an ancient idea that the sky and everything in it moves around the Earth. And if you think about, the day-to-day, we all probably were taught in our, primary or secondary school that the Earth rotates on its axis. But back in the day, they didn't know that. And so all they had to go by was what they saw in the sky. And they saw that every day the sun would rise and then the sun would set, and the moon would rise and the moon would set, and the stars would rise and the stars would set. And it looked like everything moved around the earth. And so this is kind of the idea to explain that, right? There's this celestial sphere, and the earth is stationary in this conceptual model, and the sphere rotates around the earth. Right now, there are some important points that we need to address on this model. So Jasmine, when you say this is where everything orbits around Earth, could you elaborate what you mean by that?
Yes. So in that yellowish greenish part in the last image, I'm imagining that's where like the moon and sun would orbit around Earth.
So that is a good point. That is not the case. That is not where the moon and sun orbit. But
Okay.
that green disk is what's called the celestial equator. So you see this yellow line that runs through the Earth? Okay. So this is Earth's rotational axis. And if you look at where the yellow line connects with the top part of the Earth, right over where my mouse is, that's Earth's North Pole. And at the bottom, that's Earth's South Pole. And this sort of shadowy line that's cutting the Earth in half, can you guess what that is?
The equator.
That's Earth's equator. And if you take that ring around the Earth and you sort of project it outward onto this sphere, it makes a disk, right? It makes this like two-dimensional disk surface that cuts the celestial sphere in half.
Okay.
So this upper part, let me see if I can maybe draw some lines in a certain color that might make it easier for everyone. Let's get the pen out. Okay, so these lines up here this top part, this is the northern celestial sky. Right? And on the bottom half of the Earth, the part that I didn't highlight in red, that is the southern celestial sky. If you take Earth's North Pole and you project it all the way to the top of the celestial sphere, that spot on the celestial sphere is called the North Celestial Pole. Basically, we just throw in the word celestial, and that makes the difference. At the bottom, you see where the South Pole's projection onto touches the celestial sphere. This spot in the sky is the South Celestial Pole. And the celestial sphere appears to orbit around those 2 points, around those poles.
I see now. Thank you for clarifying.
You're welcome. That was a good question. All right. So again, if this red line that I just draw around the Earth, that I just drew, is Earth's equator, and we sort of extended that line outward onto the celestial sphere, right, we get this green disk, and that is the celestial equator, which separates the northern and southern parts of the sky. Okay. So here are the definitions. You can copy those down somewhere. Maybe that'll be useful for you at some point. Hopefully it will. So we can think of this sort of from two perspectives, right? We can think of this from the perspective of what we know actually happens, which is that the sky, the celestial sphere, doesn't move. It's the Earth that rotates on its axis inside of the celestial sphere. All right, so you can imagine here, you know, if we could like sort of like twist this this thin yellow rod and get the Earth to spin from this perspective, we'd see that the Earth is spinning from I guess you kind of, again, you kind of have to have a little bit of spatial understanding here. But imagine that we were at the North Celestial Pole looking down onto Earth. Right, looking down onto Earth. We would see Earth orbiting counterclockwise. Right, if we're looking at it from the top-down view, the Earth would appear to orbit counterclockwise. But from the Earth's perspective, if the Earth is the thing that's stationary, you would get the same celestial effects if the celestial sphere were moving clockwise. Right, so whether the Earth moves counterclockwise or the celestial sphere moves clockwise, both of those are ways of explaining what we see on the day-to-day basis in the sky. So far, are you all with me here? Okay. Okay. Now remember, I said that I was introducing two things, right? I said I would introduce the local sky and I would introduce the celestial sphere, right? So these are the two sort of skies that we're looking at. Where things start to get a little bit fuzzy is, let me go back to this. Where things start to get a little bit fuzzy is when you try to imagine the local sky within the celestial sphere. And we're going to get to that in a little bit. Okay. So when it comes to the coordinates of the celestial sphere, we don't use latitude and longitude. Okay, latitude and longitude are specific to Earth. Instead of latitude, right, the lines that run around the Earth, on the celestial sphere, the lines that run around are these lines that we call right ascension. I know I'm throwing like astronomy jargon at you right now. So I know that you're hearing a lot of words that you don't know what they are. So ask questions, ask questions, ask questions. So right ascension are these lines that sort of go, they run from the North Celestial Pole to the South Celestial Pole, and we can go around. Oh, I'm sorry, I think I may have said something backwards. Let me just start over. Let me put a time out there for a second. Let's start with latitude, the lines that run around, like the equator is a line of latitude. On the celestial sphere, we use something called declination, right? Declination is how high something is above the celestial equator. So this green line, you can see I'm sort of mousing over it right now. It says equator. This line runs all the way around to the far side and back. And from there, we can either go above the celestial equator or below the celestial equator, from the North Celestial Pole all the way down to the South Celestial Pole. All right, so this is our declination. Our declination ranges from positive 90 degrees all the way down past 0 degrees to negative 90 degrees. So just like on Earth, where the North Pole is 90 degrees north and the South Pole is 90 degrees south, the North and South celestial poles are not positive 90 degrees and negative 90 degrees respectively. But then we have this right ascension, right? Right ascension is like the celestial equivalent of longitude, those lines that run from pole to pole and they intersect, right? And so you could see, starting from the North Pole, we have all of these different lines of right ascension that meet up at the top. They sort of go around the Earth, and then you see that they meet up at this point at the bottom, at the South Celestial Pole. Instead of measuring this right ascension in degrees, we measure it in hours. We measure it in hours. how many hours does it take to go all the way around on this circle? What do you think? I know it actually kind of says it there, but if you're using your heads and thinking critically about it, you might go ahead and say, well, all the way around should be 24 hours, right? Because after one day, right, if the celestial sphere is rotating around us, right, then by the time the same line makes its way to its original spot in the sky, 24 hours will have passed. So right ascension is measured in hours instead of degrees. Yes, it's actually a little less, Barrier. It's just under, it's like 3 minutes and 56 seconds short of 24 hours. But in any case, we'll get to that stuff later. You're a moment ahead of me. Okay. There's another line here that I'm going to point out to you. It's this red ring. This line is called the ecliptic. We're going to get to what that means, but not yet. All right, we'll talk about it shortly. Okay, moving on. So when we look at the celestial sphere, just zipping back here, right, you can imagine that we're looking at the inside surface of a sphere. Imagine being trapped inside of an inflatable ball and you're just sitting there floating at the middle, okay? You can see the surface of this inflatable ball around you, but you know, that's pretty much as you can do, right? You can't, there's no, that's a weird example. I don't even know what I was just thinking just now. But in any case, we're looking at this surface around us, all right? And we can take the surface inside of this sphere and break it up into different zones, almost like you would think of like different countries, right? How countries have like defined borders. So too do the constellations, right? So you take this spherical surface and you divide it up into all of these borders. And there are 88 regions of the celestial sphere. And each of these regions is a constellation. Among these constellations are the signs of the zodiac, right? So you have, or your astrological signs, you know, you have Pisces, Taurus, Sagittarius, Scorpio, Cancer, Capricorn, so on and so forth, all right? I'm going to show you now just a quick glimpse of like how you can sort of picture what this looks like. Right, so here's, you can see Virgo, Libra, Leo, Cancer. Notice how these constellations, these ones in particular, astrological signs, are right next to each other. They actually make a line. They make a ring that goes all the way around the constellation. Right, so you could go in order around this celestial sphere, around this particular ring, and hit all of the constellation, all of the major zodiac signs. Right, but then there are others that are not part of the zodiac signs, like Corvus and Crater and Sextans and Hydra and Pyxis and, you know, and Boots and so on and so forth. Ursa Major, Ursa Minor, etc. So that is sort of the breakdown of what a constellation is. Right. True or false? Please type your answer into the chat. All stars in a constellation are the same distance from Earth. All right. Okay. So everybody here, is anybody here not familiar with the Big Dipper? Just quick show of hands. Anybody not familiar with the Big Dipper? Heard of it, okay? Heard of it's good. Okay. The Big Dipper, D-I-P-P-E-R, the Big Dipper. So let's talk about the Big Dipper, okay? The Big Dipper looks like this in the sky. If you're looking at this top right part of the image here, all right? This is the Big Dipper, right? It sort of looks like a frying pan, or as they say, a big dipper, right? Something that you could, I don't know, dip a liquid with, whatever. If this is the Earth, this is not to scale, but if this is the Earth on the bottom left, and we're sort of measuring distances away from the Earth, the nearest star, or this particular star, the fourth one in, right where my mouse is, that is the nearest star of this pattern in the sky. And then this star over here, right, this one on the bottom, that's actually one of the farthest. Oh, I'm sorry, I think I messed this up. This one, wow. This star here is the farthest from Earth, but look at how big it appears on the celestial sphere, right? It looks so much brighter than some of the other ones. And so you can't necessarily look up at the sky and be like, I can tell which stars are closer in this pattern and which ones are farther away. It's really hard to tell that, right? And the fact is that, within a constellation or what have you, the stars are at all different distances, right? They're not right next to each other in the sky. Some are near, some are far, but when you look at it from our perspective, they appear to be right next to each other. Right? How about this one? The brighter the star in a constellation, the closer it is to us. True or false? The brighter a star in a constellation, the closer it is to us. True, false, 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 false. Okay, the jury has spoken. This is a false statement, right? And so, for example, I could have a really high-powered flashlight, and then I could have my small, sort of weak iPhone light, right? And if I held the really bright powered flashlight all the way back here, even though it's farther away, it would still appear brighter than my phone, right? So just because something might be brighter or not as bright doesn't really give you the best indication of how close it is. All right, well, that's something that we're going to talk more about when we look at stars, and some other important stuff having to do with them. Okay, so now this is where some people are like, "What? Stop playing! You're lying, David." Within a constellation, there is a recognizable pattern of stars. They are called asterisms. So, for example, the constellation Orion, right? So Orion is everything within these borders, right? The constellation is the region of the sky. Remember that we said that there are 88 constellations. That doesn't mean that there are 88 patterns. It means that there are 88 regions of sky, right? Because if the constellations are just the big pattern, then what about all the stars that are not part of the pattern, right? So this yellow pathway, or this yellow cutout represents the constellation of Orion. Orion itself, these particular stars that make this pattern, which is supposed to look like the hunter Orion, you can see on the right image over here, holding up the lion's head with the club in the other hand. This is called an asterism. Right, so there's the asterism of Orion within the constellation of Orion. Orion's belt is another easily recognizable asterism. Right, so Orion's belt are these three stars. If you go outside tonight and you look into the southeast part of the sky, southeast, 60 or so degrees above your horizon, around there, you should be able to see Orion tonight. It should be a clear night. You just got to figure out which way is south, southeast. The Big Dipper, right? This pattern is not a constellation, right? The Big Dipper is part of a larger constellation called Ursa Major, the Great Bear. And but this pattern of within Ursa Major is easily recognizable, and that is why it is called an asterism. All right. So now let's see. Do I have time for this? So I'm actually going to pause. I'm going to pause here, and I'm going to cover the rest of this with the second half of class. But let me stop my share here. You know, if you think about it, Barry, or I'm speaking to your comment in the chat. You know, back in the day, there weren't like lit up cities, right? There was not that much light pollution. So anybody could look up at the sky and see all these stars. And not, you know, there were times where people didn't have books, right? They didn't have these, you know, the same types of things to keep themselves occupied. So at night, you know, they go outside and they look up at the stars, and they used to use the stars to tell stories. Right? There's a rich history of that, and you know, we'll talk a little bit more about it in the coming lectures. But yes, so that is, so I mean, they definitely did have a bit of an imagination in coming up with these patterns, and different cultures picked out different patterns, right? So not all cultures saw the same things, which is also a really interesting point. Chris, yes, there is homework due on Sunday night. There's the first problem set due. Everybody here should be able to access it. If you can't access it, I can talk you through how to do it. And then you should be all good to go. The first discussion post is now going to be considered late if it's not submitted. So please make sure that you go in, even if you missed, if you were not enrolled in the course, that's a different story. But if you did not post yet, please make sure that you get on to Blackboard and post in the discussion for week 1. It is important that you get these things done as soon as possible. Okay. Not on my end, but if maybe you could coordinate with each other, Joanna, and figure out a way to connect with each other outside of class. Yeah, absolutely. Yeah, I mean, I totally encourage you all to try to do the homeworks together. The homeworks will probably give you similar questions with different numbers, so you can all, you know, you may not have the same answers as each other, but the way to get your answers is the more important point, right? That's like the conceptual aspect of the problem solving. So yeah, I strongly encourage you all do that. I think that's a great idea. Okay, so with that, I am done. Does anybody have any questions related to the homework that they want to go over? Right, if you do not, you are free to go. And if you do, I will be here. All right. Okay. So with that, have a great rest of the day to those of you that are heading out. And if anybody has any questions, I'm happy to take them now. Otherwise, I'll just be sitting here talking to myself. All right, have a good day.
So, Professor,
Yes.
every time I click on the link where it says homework and lab, and it takes me to like something that says I need to launch it. When it launches it, it gives me like an error message saying
Okay.
no authorized session exists. This most likely causes browser blocking, third party copy, whatever.
Do you have Safari?
Yes, I do.
Okay, so go into your preferences on Safari, and I would only do this when you're working on the homework.
Okay.
But there should be an option. I think I can't remember if it's under privacy or security or something, but one of them gives you the option to prevent cross-site tracking.
Yeah, I see it. Website tracking.
So uncheck that.
Okay.
All right, because the My Open Math website needs to track your information from Blackboard when you click that link. And if you're preventing that, it's not going to open for you.
Okay, it opened finally. Okay.
Right. So that, but then when you're done, if you want to make sure that you're not like getting your information tracked across websites, make sure that you turn it back on. Okay. So that's the only annoying bit, but I trust you could figure that out.
All right. Thank you, Professor.
All right. You're welcome, Alex.
Have a good
Hello,
day.
Professor.
Hi, Yusuf.
Yeah. So last week, 2 assignments were posted, right? The discussion part, and then another one.
So the discussion post, discussion 1
Mm-hmm.
was the only thing that was posted that is due. That was due yesterday.
Okay. Okay.
All right. Then there is the first problem set,
Which is
due on Sunday.
okay.
So for some reason, okay, for some reason, I'm not sure how to get Blackboard to recognize the due dates that I created for those assignments. There are due dates.
Okay.
I have them entered in Blackboard, but they're not showing up on the calendar. So if you look in the syllabus and you look at the due dates for the homeworks and the labs, those are the correct due dates. I would put them somewhere where you're going to see them frequently so that you remember what's due. And I will do my best to remind everyone.
Okay. Because as I said, I wasn't enrolled on Monday yet, and I want to I will work on before Sunday. I will work on I will try to get acquainted with the discussion, the discussion aspect.
Right. So
participation. Yeah, that's what I'll be working.
Yeah. What I'm going to recommend, Yusuf, is that for the week. So I go back into the week 1, and it's a pretty straightforward question. It's just like an introduce yourself kind of thing and comment on 2 other people's posts. But for week 2, when you get a grade for your discussion posts, I'm grading you on your initial post and how strong of a post it is out of 3 points. You're also going to get 2 other points. One of them is for commenting on another classmate's post. And the last point is for commenting on an additional classmate's post. So since the discussion grade depends on your ability and other people's ability to comment on the posts of classmates, my recommendation is that you do your initial post by like Wednesday or Thursday of
Okay.
this week.
Okay.
That way, other people can respond to your post and you can respond to theirs.
Okay.
All right.
Yeah. Posts are due like almost every week, right?
They are due every week. Well, yeah, pretty much every week, except for the weeks that we have break.
Okay. So this week, so if I do my post for the post that I'm going to do, should I do it for this week or last week's also?
So I want you could log on right now and do last week's post.
Okay.
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 And then do this week's post by Wednesday or Thursday.
Okay then. Thank you. The instructions are already there. Or not?
Perfect.
Okay.
All right,
Okay,
let me know if you have any other issues.
Okay then. Thank you, Professor.
You're welcome, Yusuf. Have a great
Okay.
day.
You too.
Okay. Sure. Could you actually email it to me, Deanna? Right, that way, because for some reason it doesn't let me copy and paste things. Oh, actually it does. It's weird. Huh. Yeah, no, you could send it in the link. That's fine. In the chat. I should be able to get it out to everybody. Okay. So the discussion board posts are always due on Sunday night of the week. So like this morning at 8 a.m., the second discussion went up. That will close on this coming Sunday, right? So you have a week to post your initial post and comment on 2 other people. Does that make sense, Dina?
Penalty, British penalty. There's a penalty.
Hello. Okay, great. So Long, I didn't hear what you're saying. Can you repeat that?
Yeah, I wanted to ask about that first problem set. Is that due to?
That's going to be due on Sunday.
Yeah,
Yes.
but I tried opening, but I cannot open that link.
Which browser are you using?
It's Safari. It's saying
Okay.
you are currently being redirected to something like that.
Yep. Alex was just talking about the same issue. So on Safari, you have to go to your preferences on the top left. Do you know how to do that?
Safari preferences.
Okay, so I can't remember if it's in the privacy tab or the security tab, but somewhere in there it says like check to prevent cross-site tracking or something like that. Or it says prevent cross-site tracking. Okay. You have, when you do the homework, you have to uncheck that because because Blackboard and the other website, MyOpenMath, have to track your information to be able to link up with each other.
Okay, thank you.
All right.
It just opened now.
Right, so now it's going to open for you. What I would make sure you do is after you're done working on it, go back in and check that off again, because you don't want like any precarious websites tracking your information as you go browsing the web. Okay.
Thank you, Prof.
You're welcome. You're welcome. Okay. Thank you, Dina, for acknowledging that it's in the privacy section. Sophia, what was your question? All right. Okay, I'm gonna stop the recording now. Good night, everybody. All right, Deanna, I will post that to Blackboard. I'll put it in the announcements. Okay, you're very welcome. See you later. See you later. Okay, Sophia,